The U.S. Frontier supercomputer is a monument to brute force. To run its calculations, the system relies on a massive array of 9,400 CPUs and 37,800 GPUs working in tandem. Contrast that sprawling facility with Google's newest Willow chip. It is microscopic by comparison, and it operates using exactly 105 qubits. Yet that tiny Willow chip recently took on a highly complex mathematical problem and completed the calculation in exactly 5 minutes. This chart shows the true scale of that mathematical gap. If you scale that 5-minute block against this expanding timeline, the graph stretches out for billions of years, which is exactly how long the Frontier supercomputer would take to process that same calculation. The calculation in question was a random circuit sampling test. It is a specific type of problem intentionally designed to overwhelm standard sequential processing. Solving problems of this specific complexity requires an architecture that moves beyond the sequential logic of traditional processors. A traditional computer bit is rigid. It must always exist in a static, sequential state, acting as either a definite 0 or a definite 1. A quantum bit, or qubit, abandons that rigidity. It operates on the subatomic level, relying on the physical state of an individual electron. This allows the qubit to enter superposition, existing as 0 and 1 simultaneously. Think of a standard bit as a coin lying flat, strictly heads or tails. A qubit is that same coin rapidly spinning, blurring heads and tails together. Maintained in this spinning state, all 105 qubits interlink to process vast webs of calculations at once. This speed relies on a completely different logic. It doesn't process faster in a straight line. It processes every possible direction at the exact same moment. But maintaining that capability is incredibly difficult. It requires keeping that subatomic coin spinning perfectly, without a single interruption. If a qubit is interrupted, it experiences decoherence. It immediately crashes out of its simultaneous state and freezes back into a basic 0 or 1. When that crash happens, a single microscopic disruption ruins the entire calculation instantly, bringing the whole system to a complete halt. The enemies of a stable quantum state are everywhere. Microscopic amounts of environmental heat, like background radiation, or even ambient noise, will trigger a crash. This massive computational potential is useless if the hardware cannot be shielded from the heat and vibration of the physical world. When the media reports on quantum computers, they almost always show this golden chandelier structure. But this beautiful object is not actually the computer itself. This massive golden structure is a cryostat. In practical terms, it is a complex and highly specialized refrigerator. All of the intricate golden wiring and dense plumbing you see here isn't calculating anything. It is built for thermal control and shielding. The actual computing hardware, that tiny Willow chip, sits completely isolated in the dark at the very bottom tip of this massive golden structure. To protect the chip from its environment, liquid helium is pumped continuously through the structure, dropping the chip's core temperature to -273 degrees Celsius, absolute zero. Freezing the hardware to absolute zero removes nearly all atomic heat and movement from the immediate environment. It is the only way to give the qubits the complete physical silence they need to spin safely. Quantum supremacy is an exercise in extreme environmental isolation. It leaves us with one major question. Once that chip is successfully frozen at absolute zero, how does it physically communicate its answers back to the warm outside world without crashing?